Hey, welcome guys to our little bonus lesson of sorts here. Um, so to get credit for today, if you're in my class watching this, then all you have to do is show me that you participated in some way. You don't have to write down every single little thing that I'm writing down. Really, for me, I just want you to actually attempt to think about it, attempt to learn something new. This is a topic that's not normally brought up in too many math classes. However, I do think it's an important one, especially in terms of history and realizing the connections that so many different things have to math and how you can break your assumptions of the world around you about how you know things. So it's going to sound super duper silly, but I'm going to begin by teaching you how to count. Sounds really, really funny that's what we have to learn how to do, but I'm just going to do it really, really fast. And I'm going to show you guys how we do it. We count like this. We do one. And then after we have one thing, we say, well, if I have another thing, then I have two things. Okay. And we use the symbol two to announce that we have two things. And then after that, if we have three things, we announce that we have three things. And okay, I'm just kidding. I'm not going to count you how to teach you how to count all the way up to this. However, I will ask you to think about a question already. Why do we not have a symbol for 10? We have two symbols for 10, actually. We reuse a symbol from above up here. We use this 1, and we add the placeholder of 0. Let's think about this for a second. 10 is not one symbol. The number 10, which we know is, 10 fingers stacked up on top of each other, or, 10 quarters, or 10 sheep, or 10 watermelons, or whatever else you hear in your math problems that you're doing. What's up with that? Why do we not have a symbol for 10? How come we decided to stop there? Why is that? And the answer is actually pretty simple, and that's because we have 10 fingers. And people didn't know what to do after that. So we count in the system of 10, where after we go to 10, we start repeating the previous digits. However, you did not have to count this way. This is called the base 10 system. This is not how everyone has always counted. In fact, it's not how even the people who were around here before, the ancient Aztecs, Mayans, and other Native Americans, quite a big number of them actually counted in a base 5 system. We know that they counted in a base 5 system based off of the histories and other pieces of information like it. And this is how they counted. So they would count a 1, 2, 3, 4, and then they didn't have a symbol for 5. Instead, that's when they started repeating their numbers. So the next thing that they would write would be what we're writing for 10. So they're writing this 1, 2, 3, 4. I'm try to line these up a little bit better here. And this is 5. And why would you want to do this? Why is this actually more intelligent back in ancient times? Why was this more intelligent than a base 10 system? Well, I'm going to show you. Because if you're counting on your fingers here, actually, no, why don't I go over here? This is actually probably easier for me. So we can count here 1, 2, 3, 4, and then the 5. But instead of doing that, I'm going to go 1, 2, 3, 4. And then on this hand over here is where I go to 5. There's 5. Now I have 6, 7, 8, 9, 10. And then we can continue on 11, 12, 13, 14, 15. That's weird. Okay. 15, 16, 17, 18, 19, 20. So if you notice, now using only two hands, I can count up much higher. In fact, just using the 4 fingers and these 2 hands here, I can instead count up to 20 and then 4. I can count all the way up to 24 using my hands instead of counting just to 10. this is how they did it. So I'm just going to write all the way up to 10 for all of these. This is going to be a base 5 system. The symbols for here, actually, you know what? Why don't I just look these up? They had symbols for these. This is an interesting little thing. This is what you can do. You can just Google the symbols for Mayans here. Symbols for Mayan numbers. I know that they had. Oh, here we are. Interesting. So they had this. These were their symbols. Apparently, they did have a solid bar for that. So they would go 1, 2, and then they use 3 dots, and then they'd use 4 dots, and then they use a solid bar for the 5. It looks like. And then after that, they start adding on top of the bar. So every bar is kind of acting like that other finger on my hand there. So when they got to 6 over here, which we're going to write as 1, 1, they'd have the bar and then a single dot. And then 7, which is going to be 1, 2, is going to be, a bar with 2 dots here. And so on and so forth. And actually, it's somewhat interesting. I'm going to zoom out really quick. We're going to count a little bit higher just so we can kind of see how these numbers work, so we can understand a couple number of powers here. We're going to go 13, 14, 15. What in the world? What am I talking about? Because we had 6, 7, 8, 9. And when you don't have a symbol for 5, there's no symbol for 5. Because there's no symbol for 5, we immediately jump up 2, and there's my 10. So 11, 12, 13, 14, 15. Continuing on, we're going to keep going. 16, 17, 18, 19, 20, 21, 22, 23, 24, and then 25 is 100 because I don't have a symbol for 5, so I'm adding the same way like when I get to 99 here, dot, 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 when I get to 99, when I'm counting up here, I don't have a symbol for that 10, so I have to start adding in placeholder values. I don't have a symbol for 5, so I have to add placeholder values when we get to 25. In fact, the base with 2 zeros is 25. You can continue this line of thinking by saying 1,000, for instance, is the same thing as 5 to the 3rd power, because we have 1, 2, 3 zeros. 125. Okay, so you're saying, well, Mr. Richards, that's all well and good. That's interesting, but I don't really care because that's just what the ancient Mayans did, and nobody counts like that anymore, and that's useless information. And you're, yeah, probably right. But let's do another type of base number, because they weren't the only people to have a different base system. The ancient Babylonians, total other side of the planet, had a different system that actually persists to this day in certain parts of the math class and in certain parts of navigation and the world around us. They had a dual base system. They used base 12 and base 60 at the same time. What in the world am I talking about? They did a base 12 / base 60 at the same time. So this time, it's going to take a little bit more thinking, a little bit harder to do. So I'm going to put my fingers like this on the table. Here's how they counted. They would count using the joints on their fingers. They would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then when they got to the 12th number, that's when they got 1 on the other hand. And then when they start getting to 13, say now they've written down the 1 number on the hand, and they start counting the knuckles again. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and now they have 2. And if you do that, that's 12, 24, 36, 48, and when they fill up an entire hand, that's when they got to 60. And they would use a little counter to say, okay, you know what? I have a 60 is an entire hand. That's a hand. And that's a hand, and this is the knuckles. So if you had a whole hand of knuckles was 60. And that's how they counted. So they had symbols all the way going up to 12, and then they had a separate symbol going on to the hand. So theirs was a little bit confusing because they didn't realize that you could just have, a single list here. They had one symbol for this and one symbol for that. Now, what's so great about 60 and 12? And where do you guys know about 60 and 12 in your day-to-day lives? Just think about where you see the numbers 60 and 12 literally every day. And if you can get away with seeing the numbers 60 and 12 somehow, then, well, obviously what's happening is you're never looking at the time, because there are 60 minutes in every hour. There are 12 hours in half the day, 12 hours on the clock, 24 hours in a full day. The whole reason we have that whole 12-24 system, that 60 seconds in a minute, all that stuff, all the 60 and the 12 is because of the ancient Babylonians counting this way with their dang knuckles. That's the whole reason we count this way and think this way. Why did it persist though? Why did it stay for such a long period of time? Let's look at this. Let's think about this. What you can do is you can take something that has a certain number of parts by 60. 60 is called a highly divisible number. You can do 60 and you can divide that by 2, you can divide it by 3, you can divide it by 4, you can divide it by 5, you can divide it by 6, you can divide it by, can you divide it by 8? I don't think 60 divides by 8. No, it doesn't. But you can divide by 9, you can divide it by 10, divide it by 12. Lots of numbers here that end up working out for dividing by 60. All those numbers evenly divide into 60 here. There's 30. And if you go up further, 360, you can actually Google this number. I wonder what the word is for 360. Is it highly divisible or super divisible? Super divisible. I gotta look up this word. Superior highly composite number, according to math here. Oh, and 60 is actually considered that. It's considered a superior highly composite number, highly divisible. Anyways, that's not too important. But I wanted to look it up. 360, you see this all the time in circles. And why? Because it's 6 of these 60s. We see this all the time, quite a bit. The whole reason we got these 12 hours in half a day, 24 hours in a day, 365 days in a year instead. But all these numbers that revolve around 60 and 12 is because of those ancient Babylonians all those years ago decided to start counting on their dang knuckles. And when they realized that the counting on your knuckles and going up to 65 times went through an entire year, when they realized that, they were convinced that the gods had come down and decided this, and that's the reason why that you had 3 joints on your hand, was so that you were able to count it, and they thought all of this was predetermined by their all-powerful gods. Crazy stuff. But again, no one really counts that way anymore. Yes, we still use their numbers because it's interesting, because it's this highly divisible system, but it's not what we do in the day-to-day world. There is a very, very important one that we do use in the day-to-day world if you ever want to go into computing, and that is the base 2 system. Why is the base 2 system so important? The way computers work is that they have a series of, I believe they are called transistors, and these guys can have a setting of 0 or 1. Every single one of these little guys can be set to be either on or off. It either has an electrical signal, the 1, or it does not have an electrical signal, the 0. It is either off or it is on. Every single one of these guys that is either off or on is called a bit. A single bit is capable of being on or off. When you happen to have 8 bits together, so if you have 8 bits, 8 zeros are 1. So for instance, if I wrote 1 0 1 1 0, that's 3 4 5 6, 7, 8. If I wrote that right there is called a byte. You might have heard of bytes before. If you've ever purchased a cell phone and it has 128 gigabyte storage, that's because it can hold 128 billion. It's actually a little bit more than that, but 128 billion bytes. So where does base 2 fall into this? Well, if you notice, it's all zeros and ones. If I counted, always has been. If it's always, I got a face for that one. It's always been zeros and ones. So what is this all about here? So if I were to start off counting off at 0, 1, 2, 3, 4, 5, 6, 7, 8. Now, this is the part of the video where I'm going to finally say, okay, you know what? Honestly, you should try to figure out the next couple of numbers. I have counted up to 8 for you. I would like you to try to count up to, say, like 16 maybe. So maybe pause the video for half a second and see if you can count up to 16, because I've counted up to 8 for you. See if you can get a little bit higher than that. A way to check your work, by the way, when you do it, is this guy right here. 0 is 2 to the 0 power. That one's 2 to the first power. This is 2 to the second power, 4. 2 to the third power down here, that's 8. That's how you can check your 1, 2, 3, 4, 5, 6. Sorry. 0, 1, 2, 3, 4, 5, 6, 7, 8. All right. Hopefully you paused the video. If you didn't, well, I'm going to keep on going. Here we go. We got 9. And then 10, 11, 12, 13. Oh, I missed one. What did I do? I made a mistake. That was 8, 9, 10. Oops. This would have been... Oopsie daisy. Man. Okay, so 1, so this is 8, 9, 10, 11, 12, 13. So 1, and then 14, 15. Finally, we did it. 16. 2 to the 5th power. Okay. Oh my gosh. It took forever to get there, all the way up to 16. So this is how all computers are run, though. Every single computer operates on the system of these zeros and ones all the way up to, and again, a single byte with all of these zeros and ones. How many different values can it take? Well, because it has 1, 2, 3, 4, 5, 6, 7, 8 slots to fill, it can fill up 2 to the 8th power different values. That happens to be 256. In fact, that 128 gigabyte I was talking about before, that's 2 to the 7th power. Every single one of those values that you ever get sold as a hard drive or something like it, or a phone storage or anything of the sort, has to be a power of 2. This is kind of just the way that the universe exists. This number of 256, though, this 2 to the 8th equal 256, is highly important in the history of computers and video games. So just as a small little side of interest here, off to the side, there's this cool thing. I just Googled color hex calculator and found this website, w3schools.com, and it has this cool little hex calculator. And let's talk about what this is. So what happens is the first computer programs that created color had 3 situations: the red, the green, and the blue. And the red, the green, and the blue could all hold values between 0 and 256. But you can't even put 256 in here. If I put 256, it becomes an FF. What? If I put a 210 in, it becomes an FF again. Something is wrong over here. Okay, so maybe we haven't learned quite enough yet. What in the world? Because I forgot to teach a little bit of an extra thing. If this right here, 256, is such an important number, we need to have another way of arriving to it so we don't have to take so long filling in these values. Because if you really, really wanted to program something to say 210, for instance, it would take you quite a bit to figure out where all the zeros and ones go. There is a way to do it. I can show you that later if you'd like. Just have to ask later. But instead, computer programmers started talking in base 16. This is also called hexadecimal. By the way, this base 2 is also called binary. So, yeah. Anyways, this base 16, how they count here, the first couple numbers are basic. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You're probably thinking, oh, thank goodness, but now 10 is the letter A. Great. 11, 12, 13, 14, 15 is that, and then 16 is when you get the 10. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay. Hopefully you're getting the point of what's happened up all the way out here. But the idea is every single number that is filled up, there are 16 symbols. So by the time I would get up to 100, that's going to be 256 because that is 16 squared. And again, that is still a power of 2, by the way. Specifically, I could rewrite that as 2 to the 4th power squared, which is, like we said before, 2 to the 8th, which we did earlier. So this 256, all these zeros and F's, go back to this little calculator I was talking about before, because I forgot to mention it, but I could say something like, how much red do I want in it? Well, if I mix like red and blue, I get purple. So if I made it totally red and totally blue, there's my purple, or I guess more pink. But if you have all the colors mixed together, by the way, it shows up as white. And if you have none of the colors, it shows up as black. And every single computer color here is a mixture of these three, or it used to be. They've actually updated the programming since the olden days there, but they no longer have the they no longer are forced to do this for computers. The days of the hex colors have passed. However, there are still plenty of things that do it. For instance, if you ever end up designing I don't know, an iPhone game or something, they still use the hex colors. I wonder if they still do, actually. I wonder if with the new fancy schmancy iPhone 12 thing, if they still do that. I have to look that up. Anyways, I hope all this stuff has been somewhat interesting, but I would like you to show that you've kind of had some version of understanding of actual practice. So let's see if we can do some problems. Some problems to make sure that we actually had some kind of real memory of what we were doing here. So let's say write the number and let's say 43 in, and I would like it in base 10, base, let's say 2, base 5, base 12, excuse me. I'm going to put a little question mark on that one really quick. And let's just do that. Base 10, base 2, base 5, and base 12. So base 10, you're done. That's 43. No real extra thinking involved. What about the other ones here? So can we write this in base 2? How can we do this intelligently without It's taking all the time in the world, like we were doing over here, where we had to take our time to get through every single one of these numbers. How can we do that? Well, we got to remember some of the tricks that I was talking about. That we know that 2 squared, for instance, would be written as 100, and that's 4. 8 is 2 cubed, and that's 1000. And then 16 is 2 to the 4th, which is 10000, 4 zeros. 32 is 2 to the 5th, 1000000, 1 2 3 4 5 zeros. And then over here, 64 to the 6 would be 1000, 1 2 3 4 5 6 zeros. Okay, so I said 43. So the number is in between 32 and 64. The goal on these questions is to write it in sections of 2. Because 43, what you're really doing with that number 43 is you're saying it is 40, and then it is also 3 more. You're saying it is 4 of the tens. Really, that's what you're doing. You're saying it's 4 tens and 3 ones. That's actually what you mean when you say it is 43. So how do I get to that 43 in terms of these powers of 2? It is 1 of the 32s. I do not need a 16, because if I went to a 16, 16 would take me all the way up to 48. That's too much. But it is also 1/8. So this 32, by the way, is 10000, 1 2 3 4, 1 2 3 4 5, 1 2 3 4 5. The 8 there is 1000. Okay. There's 32 and 8. That's 40 so far, and I need 3 more. So I can't add a 4. That's still too much. So I can add a single 2. So that's 10. So I'm at 32, and 8 is 40, and then 42, and then actually 1, 1. And that's how we do. We're going to add it up. We got a 1 there, a 1 there, a 0, a 1, a 0, a 1. Now we can go double check to see if we were right by doing a little computer thing. You can just go 43 to binary. Come on. 43 to binary, and there it is. The 101001, just as we suspected. Oof, was that a lot of effort? Let's talk about it one more time, what we did. Let's talk about it one more time before I throw you off to the wolves to try to figure out the 5. So, the base 2. We want to figure out how do you write 43 in base 2. So we have to figure out how many powers of each kind. We had 132, an 8, a 2, and a 1, because 32 plus 8 is 40, 42, 43. We had to add them up until we got there. There's our 100,000 and 1,000, a 10, and a 1, and we simply add it up, kind of just following the digits there. That's it. There's our 43. Let's see what we can do for base 5. So for base 5, we're going to follow exactly the same concept. We're going to start off by writing all of our powers of 5. The first power of 5 is 5, the second power of 5 is 25, and the third power of 5 is 125. And remember, we are going to write that power of 5 as a 10, and this power of 5 is 100, and this power of 5 is 1,000. And we're trying to write 43. 43 is in between 25 and 125. So we have to write it using 125. So we have 125. And then how many 5s do we have? So in order to get up there, if we had 1 5, it would be up to 30. Another 5 would be up to 35. Another 5 would be up to 40. So we have 3 5s. And then after that, we have, that's taking us up to 40 so far. And we need to be up to 43. We also have 3 1s. So that 125 is 100. The 3 5s is a 30, and the 3 1s is a 3. 133 is our 43 in base 5. By the way, it's typically notated by putting parentheses around it and the number of the base like that. So like this one would be like this, you know, with a little 2 down there, little parentheses, little 2. What about base 12? So base 12 is where things get a little bit more complicated because you need an extra symbol of some kind. So we're gonna have to remind ourselves that counting up to 12 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12 is where we start repeating ourselves at 10. So uh, you know, um, 12 is equal to 10, and then 12 squared, that's 144, which is um, our 100. So we get up to 43. How many 12s are going to be in 43? Well, there are going to be 3 12s because it goes up to 36 that way, and then 7 1s. So that's going to be simply 30 and 7. 37 is how you write 43 in base 12. Weird, weird, weird. But ultimately, what's more important for your future understanding of everything is doing things in base 2 and base 16. That's kind of how computers work. Lots of that in base 2. So I am going to have you guys try out some more in base 2. Let's do that right now. Let's do some base 2s. We're going to have one more question go in one way, and then we'll go the other direction after that. So let's say let's want to write the number, how about 95 in base 2. Let's repeat this process again. First thing to do is to write out all of the powers of 2. So 2 to the first power, which is just 2. 2 to the second power is 4. 2 to the third power is 8. 2 to the fourth power is 16. 2 to the fifth power is 32. 2 to the sixth power is 64. 2 to the seventh power is 128. And because 95 is in between 64 and 128, we're going to start here by saying we're going to use 164. How much is left over? Just cheat. Use a calculator. Use your calculator. Not a big problem at all. I know we're doing a little bit of thinking here, but we don't need to. Just calculator it out. Here we go. We do 95 minus 64. How much is left over? We have 31 left over. So if we have 31 left over, we don't use any 32s. So we can't use any 32s. So we have 164. By the way, that has to have 6 zeros added to it. Oh no, I'm gonna run out of room in my paper here. Let's move my calculator. Whee! Come on, my mouse not happy with me. Okay, and we're gonna go ahead and do 1, 2, 3, 4, 5, 6 zeros. Maybe you can put commas in between so we can see where things are. So we had 164. Once we've taken 64 away, we have 31 remaining. The 31 remaining, we have a 16 there, so we're also going to have 116. Our 16 has 4 zeros on it. So 1, 2, 3, 4. There you go. There's our power of 4. Maybe put that comma in there again. And we subtract 16 away. How much left over is 15. So again, we don't have a 15, but we do have an 8. So we have 1 8 then, which is equal to 3 zeros right there. So minus 8 more, which is 7. And now we can't take away an 8, so we take away a 4. So we also have 1 4. And that guy is going to be 1 with 2 zeros. Subtract the 4 away. We'll have 1, 2, and then you have 1 left, so you have 1, 1 as well. Adding this all up, we have a 1 there, 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 a 0, and a 1. Boom. That guy is our 95 in base 2. I'm going to do it one more time for you before I really want you to try it all on your own. Let's see if we can figure out some other numbers in base 2. Let's do it. Let's say we had instead, how about we do 51 in base 2. So same exact place we're going to start up. We're going to write these powers of 2 out. If you already have the powers of 2 written out off to the side of your paper, you don't have to keep writing them down. You can just keep a table of values there ready for yourself. So you got 2 to the 1 is 2, 2 squared is 4, 2 to the 3rd is 8, 2 to the 4th, 16, 2 to the 5th. Ugh, I didn't even write that as a power. It's so ugly of handwriting. Equals 32, 2 to the 6th power is 64. All right, so 51 is in between 32 and 64, so we can start off by saying we're going to have 132. And that's going to be 132 is 1, 2, 3, 4, 5 zeros. There's 2 to that 5th power. 51, subtract away that 32. Where'd my calculator go? Here it is. 51, take away that 32. Now I'm at 19. So that does have 116 left over. That 116 is 1, 2, 3, 4. Right there. And then after you take away 16, you'll have 3 left. So that'll be 1, 2, and 1, 1. So that's a 1, 1. What is that? 0, 0, 1, 1. There you go. It's 51. Please note you can always use Google to check your work here. So you can do like 51 in binary, and it will automatically convert it to you. There's your 110011, and it will auto convert for you. Hopefully that was interesting enough. So as practice for yourself, and you can use Google to check your work. I don't think I need to do 4 or 5 more in front of you, but just as practice, just to see if you really got it. Try it out. See if you can try and write out 35 in base 2. And there's 35 in base 2, and also write up maybe 74 in base 2. So try out those 2 problems kind of on your own. See if you've got it. I'll let you pause the video for yourself and try it. I'm not even going to write the answers. I really want to see that you actually attempt to do it on your own. Just do your best. Any version of thinking is okay. But it's also interesting to see if we can go backwards, because going backwards is actually really, really, really fast. That's the good news. Going the other way is super quick. I remember kind of in class one of these other days, one of my students was making a joke about me making this video up because I told them that you could just write all your answers as 1s and 0s. And he wrote something obnoxious like 1, 1, 0, 1, 1, 0, 0, 1, 1, 2. You can't write another 2 there. Just 1, 0, 1. Okay, convert this guy. Base 2. Convert that into into a base 10 number. So actually write this as a base 10 number. This is just going to be that 1 right there. That's 2 to the 0 power. This guy we can skip. So that would be that's 2 to the 0, 2 to the 1. Right here, that's 2 to the 2. This would be 2 to the 3rd, 2 to the 4th. So every single position here is simply a power of 2, possibly. If it's a 1, it shows up it's an on position, kind of like we were talking about with those computers. If it's a 1, it's an on. If it's a 0, it's an off. So the 2 to the 11th is on. So it's 2 to the 11th plus 2 to the 10th plus 2 to the 9th is skipped because it's off. 2 to the 8th plus 2 to the 7th plus 2 to the 6th is off. 2 to the 5th is off. 2 to the 4th plus 2 to the 3rd plus 2 to the 2nd. 2 to the 1st is off, plus 2 to the 0. And we'll just type this into our buddy Google because I do not want to even attempt to do this one by hand. Where'd my calculator go? Here we go. So just you guys can actually see I'm typing it in. We're doing 2 to the 11th plus 2 to the 10th plus 2 to the to the 8. You know what? Let's be lazy here. Let's copy the 2 to the power. Actually, let's copy the plus 2 to the power. Here we go. So plus 2 to the 8th, plus 2 to the 7th, plus 2 to the 4th, plus 2 to the 3rd, plus 2 to the 2nd, plus 2 to the 0. Then type all that in. Holy moly. Turns out that that number in binary is 3,485. And we can actually double check that by typing in 3485 in binary and have it do it. Let's check it. 11011001101. Perfect. That's how it is. So for your last little practice problem of the day, we're hitting up 42 minutes. I said 45 minutes about. So, and if you spent some time doing those other questions and doing this last one, just attempt it. See if you can do it. Convert 1111001 to base 10 for me. Go for it. Try it out. Hopefully this was an interesting video for you. A little bit of an extra topic, not really required, but hopefully somewhat interesting. Yeah, I will see you guys next time. Have a great rest of your day, and hopefully it was interesting enough. See ya.